So I've been kind of dragging this video out for a while, but let's see. Basically what it covered so far was first the tangent problem, which was basically moving one point really close to another point, but never actually touching it. And then you can get an approximation of its the equation of the secant line, and then you can actually find the tangent line. And then that introduces limits. And there's the area problem that he couldn't really do now because it uses other stuff that is later on in calculus. But that also was the idea of limits with the rectangles, making like infinite rectangles pretty much, making it super close to find the area. And I watched a little bit of this, but I'm just going to rewatch this section on solving limits. So
Alright, so if you remember from last time, we're talking about limits, and what we're realizing is that a limit basically says, or asks the question, what is the function doing, what's the value of the function doing as x approaches a certain number? Now, do we ever care what happens when x gets to that number as far as a limit is concerned?
no.
No, not really. Just what's the function doing? Where's it getting close to as we're getting close to that x value? And that's the idea here. So when we're talking about the limit of x minus 1 over x squared minus 1, that's our function, we want to find out what happens as x approaches 1. Now, why can't I figure out what happens when x equals 1? Tell me that.
Undefined.
That would be undefined, right?
Yeah.
As a matter of fact, it makes both the numerator and denominator 0, and that would still be undefined. We found out that is that a whole or an asymptote? Do you remember?
It's asymptote.
That's a whole. That's going to be a whole. That
Oh, wait.
ultimately this
What is it? That's a whole whenever. Wait, let me maybe explain something.
function has a whole. So what we want to find out, though,
What is that? I think whenever it's 0 over 0, it's a whole. Whenever there's something on the numerator, but the denominator is 0, it's an asymptote.
is what's the function doing as we approach that certain
I want to make
value?
sure of that because I don't want to forget that. Whole versus asymptote. Wholes occur when factors from the numerator and the denominator cancel. When a factor in the denominator does not cancel, it produces a vertical asymptote. Okay, these cancel. I see. But what do you get whenever you plug something in to make it a whole? Watch a quick Brian video.
So let's do these one at a time. So one question I'll ask you is, we should hopefully be able to identify the domain here. We know that the domain is going to be all real numbers except for -1, because that makes that 0, and 3, because that makes that 0, right? You guys kind of see how, like inspection, we can kind of do this a little bit quicker. But anyways, that's not the point here. Well, my point
So this one's a whole, this one's a vertical asymptote.
is that there's going to, since the domain is undefined at -1 and 3, because that's what makes the denominator equal to 0, those are a discontinuity. Yes? And we talked about two types of discontinuities and 3 kind of labels for them. It's going to be removable, non-removable, and we could be a vertical asymptote, a whole, or a jump. So we are not going to refer to jumps. Right now we're just going to talk about wholes and asymptotes. So how do we know then if our discontinuity at -1 is that a whole or is that a jump? Our discontinuity at -3, so we could say, yes, those are discontinuities because those are the numbers not in the domain. Yes? All right, so what are they then? What are they? How do we know? So the basic rule, guys, is if they divide out, don't you guys agree x minus 3 divided by x minus 3 is 1? So it can be simplified. If, guys, if they can be divided out, this is what we call a whole. Okay? Which obviously we know is removable. On the simplified version of this graph, we still have x over x plus 1. This never got removed. It's non-removable.
Okay, hold up. So if I plug in -1, -1 minus 3, -1 plus 1, -1 minus 3. Okay, and then these cancel out. There's a -1 on top. Okay, I'm confused now. Alright, it's a whole if it cancels out, I get that. But there was something else that he did in another video where it was like you plug in the number and you can mathematically like see it another way. I don't know. Whatever.
All right, so if you, as x approaches a certain number, now, do we ever care what happens when x gets to that number as far as a limit is concerned? No, not really. Just what's the function doing? Where's it getting close to as we're getting close to that x value? And that's the idea here. So when we're talking about the limit of x minus 1 over x squared minus 1, that's our function, we want to find out what happens as x approaches 1. Now, why can't I figure out what happens when x equals 1? Tell me that. That would be undefined, right?
Yeah.
As a matter of fact, it makes both the numerator and denominator 0, and that would still be undefined. We found out that is that a whole or an asymptote? Do you remember? That's a whole. That's going to be a whole. That ultimately, this function has a whole. So what we want to find out, though, is what's the function doing as we approach that certain value? Now, one way we figured out, the only way we figured out these limits, is to make up a table. And this is kind of the elementary way that you discover limits right when you first learn. Now, towards the end of the day, I'll teach you some better ways on how to do this. For right now, though, I want you to see what happens with the function and with the limit. So when you are finding these, and your homework's going to ask you for that, find the limit of this function by making a table of. When you do that, you have your x values on the top, you have your f of x values on the bottom, in this case, x minus 1 over x squared minus 1, and you start with the number you want to find the limit of, the number that you want to find the limit of the function where x is approaching that certain value, put that in the middle. So for instance, you're going to put 1 right there. And really, I don't want to know what that is, because you can't plug it in anyway. What we want to find out is what's happening from both sides. Is it going to the same value? You follow me on this? So what you need to do now, put these numbers in order because it is a number line. You don't want to have like I see a lot of mistakes on this. I see a lot of people do this. Okay, well, I'm going to start at 2, and then I'm going to go to 1.5, and then I'm going to go to 1.1, then I'm going to go to 1.0001. Right. Do you see how that's the wrong way to do it? That's going to show you one direction, but it's the wrong direction. You need to have these numbers reversed so that this is just a little bit past 1. We're coming from the right-hand side. So if you want to find out where it's coming from, don't have 2 right here. Have 2 over there somewhere if you're going to do that. All right, so these numbers that we have next to 1, they should actually be the numbers that are close to 1, all right, not the other way around. Are you following that? Nudge your head if you're okay with that. So we don't want to have the smallest numbers over here that are the ones that are closest to 1 over there. We want this just like a number line would look. So here, maybe we do start with 1.5, 1.01, 1.001. Make it really close to 1. Now the other way, I'll probably want to start with 0.5, right? I want to make it symmetrical at least a little bit. So where's 0.5 going to go? Is it going to go by the 1 or over here on the left-hand side?
Left.
Left-hand side. Now I want the numbers that are really closest to 1, well, the closest to 1. That's going to show me the trend.
Very true.
So 0.5, maybe 0.99, and 0.999. What I'd like you to do right now on your own, take out your calculator, find those numbers. How about this? The people to the, let's see, this is your left. The people to the left side of the camera, do these ones, okay? People to
Couldn't you cancel out one of these? And then you'd just be finding 0.5 plus 1? Is that it?
the right side of the camera,
Or are you not allowed to do that?
do those ones. Can you do that for me? So plug into the function, tell me what you're getting out.
I know there's a way to do this on it. You know? Have you started to find those numbers? Does anybody have this one yet? 6 point.
6 continuing.
Does everyone got that one? The same one? 6.6666 for everyone?
Guess you gotta plug it into the
6.67. How about
original.
the 0.99? Did anyone find that one? 0.99.
Or wait.
Okay.
No, I don't
Get a
think.
double check on that 5.
I think you have to plug it into the original.
How much?
0.503.
0.50. How about for this one? That's the right one? Let's double check that one. 0.99 minus 1, that should be pretty small, negative something. One more double check. What'd you say it was?
At 0.5 and then for the first one, 0.6. Yeah, 0.6.
0.66. Is your calculator scientific notation by chance?
No.
Why don't you guys figure out your stuff, all right? I'll come back to y'all. This side. Try this side. Can you give me 1.5?
0.4.
How much?
0.4.
0.4? Can you give me 1.01?
0.497.
How much?
0.497.
0.497? 0.497? I'll take it. Okay, can you give me 1.001, please? 1.001.
0.499.
0.499?
Jeez, that side
Okay.
was killing it.
Interesting. I'm guessing the 6 was probably not all that accurate. Let's try that again.
So yeah, if you plugged in 1, you're not going to get anything. So the only way to solve this is to plug it into the table. At least that he's showing right now. He said he's going to show another way.
I don't know what was on side.
Makes sense.
Ah. So 0.6. Okay. Give me 0.99. Point what? 0.503? Give me 0.999. 0.5002? Now, do you see the trend to which this function is getting close to? Can you see it? What number is it getting close to from the right? What number is it getting close to from the left? That's why you put it in this order so you can see where it's approaching from the left and from the right. If it's the same number, if this is getting to 0.5 and that's getting to 0.5, you'd say, okay, that limit exists and that limit is 0.5. Are you following me on this? So the limit right here would be 0.5. And that's how you use a table to figure that out. Now, of course, this was a pretty mind-numbing task, right? Who wants to plug in 1.001 and do all this for a whole bunch of numbers? Do you want to do that? No, I don't want to do that either because it's boring, right? We're going to find some better ways to do these limits in the next section. For right now, though, I need you to get to understand what a limit is. A limit asks, what's the function, the value of the function do as you get closer, as your x value gets closer to that? What's the function's value do? What's the function's value do as your x value gets closer to that? From both the left and the right. If it's to the same number, the limit exists, and it's that number. Raise your hand if you're okay with this so far. Now, are there ever cases when the limit doesn't exist for a number? I want you to look at this, all right? We're going to talk about something called one-side limits. And the question is, what's the limit as x approaches 2 of f of x? Now, what we've had on the board already is what's called a right-sided limit and a left-sided limit. You have this kind of intuitive idea, right? In order for a limit to exist, it's got to go there from both sides. Does that make sense to you? It's got to get there from both sides for a limit to exist. So from the left and from the right, it has to be the same number. I want you to look at this thing. Which way would be from the right? Over here or over here? Option 1 or option 2? From the right would be this way, true? We can actually have right and left-sided limits. So here's how you write that. A right-sided limit
What?
in our case would be a limit of our function as x approaches whatever value you're talking about. In this case, we're talking about the value 2. Do you guys see where the 2 is coming from in this case? We want to find out when x approaches 2. And how you say from the right-hand side is you put a little superscript plus. That means from the right. So in general, you'd have
Alright, so we got right-sided.
this. You'd have a limit of f of x as x approaches a some number that I give you from the right. That says a right-sided, one-sided, right-sided limit. Nod your head if you're okay with that. So plus means from the right. You all right with the plus meaning from the right? What do you think a left-sided limit is going to have? Ooh, you guys are geniuses. Exactly. Yeah, left-sided limit. would be a limit of f of x, sure, as x approaches a certain number. In our case, our certain number is 2. And that little minus or negative is from the left. In general, we'd have the same situation, only from the left.
Whoa. Why is my OBS doing that? Hold on. Good now? Yeah, okay, we're good.
So let me ask you a question. Can you find the limits, both right-sided and left-sided, of this function? Let's try that together. Here's what the question, I'll do this so you can understand it. Here's what the question asks. What is the value of the function as x approaches 2 from the right for right-sided and from the left side, okay?
What's the value? As it approaches, it'd be 2, right?
So follow the function along.
Wait, as x approaches 2. Approaches 1. And -1 from the right, -1 from the left. Or wait. Yeah.
I need you to tell me what the height of my finger is. What's the height of my finger when I get really close to this value along this line? So this is from, am I going from the right or the left in this case?
Right.
From the right. From the right. Okay, it's always from the, it's not to the, it's from the right. So from the right, the height of my finger is, okay, I'm a little above 1, a little above 1. What's the height of my finger going towards as I slow down?
1.
I'm slowing down. What's the height of my finger trying to get to? It's trying to get to 1. Do you see that?
But it doesn't actually
It's not
get
that my
to
finger's
1.
getting close. It's not the limit's going to be 2. It's saying what happens to the value of the function. The value is your y-axis. What's happening to the value of the function or the height of my finger as my finger is approaching in this direction, the number 2. Does that make sense to you? So here, the height of my finger is trying to get to 1 as I'm approaching 2 from the left. That's what I said. From the right. I'll edit that out. You won't even know. Beep.
Yeah, I'll totally edit that out.
Just kidding, I'm not going to edit that. It's going to be on there forever. Yeah, so from the right. So from the right, it's going to be approaching 1. Yeah, thanks for that. You okay with that being 1? It's either yes or no. If you're not, that's okay, but I need to know. I need to have a question from you if you're not. Are you guys okay with the height of that being 1 as this function's approaching an x value of 2? So basically you're asking what's the y value when you reach your x value? All right. What's your y value when you reach your x value? So now we're going to do it from the left-hand side. What's the height of my finger, aka the y value, as I approach the x value of 2? So what am I doing? Where am I getting close to as I'm getting to 2 from the left-hand side? What am I getting close to?
-1.
-1. Yeah, absolutely. Now, here's a little note. Here's a little note for you. In order for a limit to exist at a point, the left side limit must equal the right side limit. If it doesn't, then the limit doesn't exist. Does that make sense to you? It's got to go to the same place, otherwise the limit doesn't exist. You can be one-sided, sure, here.
Wait, say that again?
The limit to exist at a point. The left side limit must equal the right side limit. If it doesn't, then the limit doesn't exist. Does that make sense to you? It's got to go to the same place, otherwise the limit doesn't exist. You can be one-sided, sure, here, here. But if it's not the same spot, then you'd say overall the limit means from both sides. The general limit means from both sides. So if it's not going to the same thing, that limit doesn't exist. So let me write that out for you, and I'll explain it. For a limit to exist at a point, we'll call it A. For a limit to exist at A, in other words, for this to happen, for you to be able to say the limit as x approaches a is some number. For that to happen, you must have this. The limit of f of x as x approaches a from the left must be equal to the limit.
It's doing that thing again. What? Why is it doing that? Seriously? Alright. Can I make a new one? Maybe this is just how window capture works.
Of f of x as x approaches a from the right.
No, I think it is. No, whatever.
It's got to happen. So let's see if that happens. What this says in plain English is this. Ready for the plain English part? Here's plain English. The function from the left and the function from the right have to have the same value. Basically, they've got to meet up somewhere. You with me on that? So let's check this out. Does the function from the right and the function from the left meet up? What do you think? Do those lines meet up? They do? They
Oh.
meet up? They come to the same point?
Yeah.
Same value, same height? Well, let's see. This limit was 1, this limit was -1. Is 1 the same as -1?
No.
So, does both the one-sided limits have the same value? No, you'd say this limit does not exist. So we'd say the limit
Oh, okay.
as x approaches 2 of f of x does not exist. This says why? This says the limits from the left and the limit from the right must be the identical number. Do you remember this example? Look up here on the board. Remember this example? Hey, you said the limit existed because that's 0.5 and that's 0.5, basically. It's coming to 0.5. You with me on that? What if this was 0.5 and that was 7? Would that be the same number? Hey, you said the limit existed because that's 0.5 and that's 0.5, basically. It's coming to 0.5. You with me on that? What if this was 0.5 and that was 7?
Nope.
Would that be the same number?
Nope.
Now, this one's 1, this one's -1. Is that the same number? That limit doesn't exist. Okay? It says that you have to have the same function value on both the left and the right. Both. Would you like another example of this?
Sure, yeah.
Why not? May as well.
You have time.
Let's practice. Okay, let's get some good practice. If you're not getting it, I need some questions out of you because you really do have to understand this before we go any further. So, here's the idea. In order to find the limit at a certain value, in this case, we're going to talk about 2 again. Do you see why that would be the interesting case here? I want to break it down to you, all right? If I asked for the limit of 3, it's not very interesting because look it. Here's the value of 3. Does the limit exist at that point? Answer's clearly yes. At 3, yeah. Look it. The function's there, the function's there, the function's there. It's all the same. Do you get me on that? That's not an interesting example. That's boring. That just says the function is completely there, therefore the limit must exist. From the right and from the left, you're coming to the same exact point. Do you get me on that? That's not interesting. If I ask you about 2, though, that's more interesting. You need to be able to find the limit from the right and the limit from the left as we're approaching an x value of 2. In math, that means this. Can you do this? Can you do this? And can you determine this? Let's see if you can.
Okay, so from the right, it's approaching 3. From the left, it's approaching 1. So it doesn't exist.
Let's see if
Limit
you
doesn't
can.
exist.
I'm going to give you about
Next
5
approach
seconds
is
between each problem to see if you can get it, okay? So right now, I want you to determine on your own, can you tell me, don't say it out loud, okay, let everyone do this. Can you determine on your own the limit of g of x as x approaches 2 from the right? Do it on your own, don't say it out loud. Give it 5 seconds. The question in English asks this. What is the y value when x gets really close to 2 from the right? That's what the question asks. What is the function value or the y value when x gets really close to 2 from the right? Well, that was like 4 people answering. Do you all not know it, or do you know it? If you don't know it, then that's fine, but you need to tell me. If you know it, then say it. Can you find out that the function value, the y value, is about 3, or is getting close to 3 when x is getting close to 2? Can you see that?
Yep.
Because you're following this along, right? You're going, okay, what's happening as I'm getting close to the value 2 along x? The y is getting close to 3. So this is how much? Okay, now I want you to do this on your own. Don't say it loud again. Find me the limit of g of x as x approaches 2 from the left. Write it down in your paper. Don't say it loud. From the left. Basically, in English, that says, what's the y value when the x value is getting close to 2 from the left? Starting from the left. What is it? 1. Did you all get 1? How many were able to find 1? Good, okay. Here's how you tell if the limit exists or not. Here's how you tell. You look at these ones. Are they the same? You sure? Yeah, one's 3, one's 1. I mean, how much more sure can you be? If those aren't the same, does that exist? If those are the same, does that exist? Yeah. I want you to know something really cool, too, about limits. Does it matter at all that that point was right in the middle of nothing? We don't care about that point. We don't care at 2. We care what's happening to the function as we're getting close to that. You see the difference? I don't care about that. It could as well not even be there. It doesn't matter. We don't care about that point. We care about the function value, the y value, as we approach the x value. So this does not equal that. Does that exist? No. Do you put D? You can really see it though, can't you? If the lines don't match up, it's not there. It's not going to happen. The limit doesn't exist. Let's do one more and we'll call it good on this stuff. Here we go. Oops.
Right now, the only question I have is, what does that even mean whenever the limit just doesn't exist? I'll probably look that up later. Because I can see on the graph that it doesn't exist, like clearly, but what exactly does that mean, I wonder?
Okay, last picture for us. I want you to try to do that one completely on your own, okay? This is h of x. I want you to find the limit of h of x as x approaches 5 from the right. I want you to find...
Alright, so from the right, it's approaching 3. From the left, it's approaching 3. And so it's approaching 3, yeah. Wait, as x approaches... Yeah, as x approaches 5, h of x approaches 3. But Wait, the point's up there. Okay, I don't know.
The limit of h of x as x approaches 5 from the left, and then I want you to determine whether or not that limit exists at x equals 5. Or do you follow the questions? And go ahead and do that. See what you get. Ooh, let's see if we did it right. Okay, so the limit of our function as we're going from the right, as we're going from the left, and then we're going to compare those numbers. So from the right means from the positive, or from the more positive, I should say, because sometimes they're both positive. From the left means from the less positive or negative, whatever your case may be. So from the right, from the left. From the right, what is the y value as your x value approaches 5? What are you getting towards? Okay, well, what about that one? Does the function actually approach that? Approach it. See, that's the difference. We don't care what it is at that number. We care what it's approaching as we're getting close to that number. You see the difference, right? Okay, so you all got, we care what it's approaching as we're getting close to that number. You see the difference, right? Okay, so you all got how much? Perfect. Let's do it from the left. From the left, what's the y value getting towards as you...
So, at x equals 5, it actually is y equals 5, but it approaches 3. So that's the limit.
Your x value is getting towards 5.
I think.
Good. Is the right-sided limit the same as the left-sided limit?
Yes.
Does the limit exist?
Yes.
Absolutely. Yeah. Why? Don't care what happens at that point. Just because this point doesn't fill in that hole, it doesn't matter. As long as the function's value is going to the same exact spot from both sides, do we care what happens when we get there? No. We don't care about that. We care about this. That limit is 3. How many people have a better idea about the idea of a limit right now? So given a graph, you can do this? Okay, cool. Hey, let's talk about that for a second. What's the one number you can't plug into that?
0.
What would happen if we discovered what the function does as we approach 0? Isn't that an interesting question? It's kind of cool, kind of interesting. What happens to the function as we get close and close to that? Let's talk about that for a second. Now, in order to talk about that, we need limits. What's the function do as we approach that? So just like we did over here, we're going to talk about a right-sided and a left-sided limit, but we're going to do it with a table. Now, what number are we approaching? I'm sorry, what was it? Where's the 0 go on our table? To the left, to the right, or in the middle?
Middle.
Because that's the number we're trying to get to. Are we ever going to be able to get to the 0?
Nope.
Now, we can't plug it in because then it's undefined. That would be a problem. So now, let's pick some numbers that are getting close to 0 from the right. Let's start at like, oh, I don't know, 0.5, and we'll work our way down. So 0.5, is 0.5 supposed to go here or here? The right or the left?
Right.
Right. So 0.5, all right. 0.01 and 0.001. Would you agree those are numbers that are pretty close to 0? Right. What are the numbers to the left of 0? What do you want to use?
Same ones but negative.
Okay, good. They have to be negative, though, because they're to the left of 0. So negative 0.5, that'll work. And negative 0.01 and negative 0.001. So let's use those numbers. Again, left side people, do the left side. Right side people, do the right side. These ones should be a little bit easier to plug in, yeah? A little bit. By the way, this is going a little bit out of the scope of this section at this point. We're talking about something a little ahead of time. 'Cause it's interesting to me, so we're covering this right now. It will come back at us later on, right? But I'd like to make sure you see it in limits at least once or twice before we get to that section. So if you take 1 and you divide by 0.5, I'm hoping that you got 2. Did you get 2? And over here you probably got, well, I'm going to be a genius about that, -2. Did you get -2? Genius. No. Geez, I hope so.
No. I divided by 1.
Okay, good. Whew. I scared myself for a second. So 2 and -2, very good. Now, how about 0.01? If you divide 1 by 0.01, you should get, let's see, move the decimal place, you should get 100. And I'm going to hope this is -100. Yes? If you divide by 0.001, that's, let's see, 1, 2, 3 decimal places. You're just dividing 1 by decimal places there, ending in 1. That should be... Let's do a little critical thinking here, all right? First question is this number getting bigger or smaller as we're approaching 0 from the right?
Bigger.
Is it ever going to stop getting bigger?
No.
1 divided by 0.000001 is going to be really, 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 really big, right? And it's going to be positive.
Infinity?
How about this way? Is it getting bigger or smaller? Way smaller, and it's never going to stop getting smaller. It's not going to a certain number. Now, the second question is, does the limit exist? Are they going to the same exact number?
Yes.
No, in fact, as we're going from the right, where would you say this is going? Because if you draw the picture, it's going like that. It's going where? Infinity. If you divide by smaller and smaller numbers that are approaching 0, keep dividing by 0.00000 forever and the little 1, you're going to get really, really huge.
Because it would look like 1's going up, then 1's going like all the way down, so they're never gonna. Yeah, okay.
Huge numbers, right? And you can keep getting smaller and smaller still. So what we would say is the limit as x approaches 0
Doesn't
from the
exist.
right of our function, which is 1 over x, is positive infinity.
Oh.
And you technically don't have
Well,
to put a plus,
from the
'cause
right it's positive infinity, from the left it's negative infinity, and then in general it doesn't exist.
infinity without that plus still means positive infinity, but I want to show the difference. Limit as you approach, I'm sorry, x approaches 0 from the left is, what would you say that would be? Is negative infinity the same thing as positive infinity?
No.
So limit clearly doesn't exist. In
Makes
fact,
sense.
you can see this from the graph. If you graph 1 over x, your calculator, whatever you graph it on, is going to look like this. That's it. You can see as we get towards 0, it's skyrocketing. As we get towards 0, it's really going into an abyss, right? So it's not going to be the same thing. But this leads us to a couple ideas. Whenever we have a limit, I'll write this up for you. If you have a limit as x approaches a from either the right or the left of some function, and you figure out that it's positive or negative infinity. I'll say it again. If you are approaching a number, right, from either the right or from the left, and it's going to infinity, either positive or negative, what that does for you is it gives you an, what's this thing called? Gives you an asymptote. Gives you an asymptote. Because you say, okay, if we're going towards infinity, as we're reaching, as if my y value is going to infinity, as my x value reaches a number, that means I have to be shooting up. If my y value is going to negative infinity, as I reach a certain number, that means I have to be shooting down. So one of those cases, it's going to be some sort of asymptote. You're never going to actually get to that point. You can't. You can't. So there are really 4 cases. I'll draw them over there so that we see them. 4 cases of asymptotes and their relationships to their limits. So the one case is what happens if we approach a from the right and we're going to positive infinity. Another case would be what happens if we approach a from the right and we go to negative infinity. Another case would be, well, what would happen if we did the both rights, right, from the right. If we went to a from the left and went to positive infinity. Or what would happen if we went to a from the left and it gave us negative infinity. Would you agree those are all four permutations, all four cases of this? In either case, we just talked about this, if your function is going to positive or negative infinity, when x is going to a from the left or the right, you're going to have an asymptote. So every one of these is going to be an asymptote. Well, that's the worst asymptote I've ever drawn.
That's the second worst.
Oh, that's not bad. Back on track. Let's kind of diagnose what these things would do. I want you to really think of what these limits should do to our function here, okay? Now, if I say x is approaching a from the right, should I start here? Or start this way?
Yes.
Am I going this way, option 1, or this way, option 2? Option 1. So if the function's approaching a from the right and it goes to positive infinity, should I be going up or should I be going down?
Up.
So this would be this type of graph. It can do whatever it wants over here. No problem, but when it gets to here, it shoots up. This is not going to be, this isn't going to be told by our limit as we approach a, all right? It has nothing to do with it. It's what happens as we get close to a. It's going to be going towards positive infinity. Let's talk about this one. Now, I know we were just coming from the right-hand side. This one's going to be going, well, not up, not positive infinity. It's going to be going down, negative infinity. Do whatever you want over here.
Wait, I think I get what it means it doesn't exist, the limit. So if it has to be approaching from both sides to one value of y. So if it's only if it's approaching different values from either side, the left and right, then there's no limit. You can say there's a limit when you're approaching the right, a different one when you're approaching the left. But there would be no limit as x approaches whatever, just in general, I guess.
But it's going to drop. It's going to be asymptotic to that line. How about this one? Can you picture what that one does in your head already? Draw a graph if you want to right now. You should be able to draw something with that. Are we going option 1 from the right or option 2 from the left?
From the left.
From the left. And should we be going up or down?
Up.
Which one? It's going to positive infinity. Up or down? Lastly, the only case we have left is from the left going down to negative infinity. It looks something like that. Would you raise your hand if you feel okay with what we've talked about so far today? All right. That takes care of kind of our introduction to limits. We talked a little bit about that. Now, for the rest of our day, I'm going to teach you how to compute limits. Because if you hadn't noticed, this isn't all that fun. I'm going to show you some better ways on how to do that. Would you like to learn that? Cool. Any questions before we go on?
Yeah, just a quick one. The two limits for both approaches and infinities, they go towards the same point, or would it exist?
The limit would exist. Yes, it would. So if we have a one-side limit this way and a one-side limit that way, and they both go to positive infinity, yeah, sure. We'd say the limit is positive infinity because it goes from both sides. Or if the limit is going both negative infinity, that would exist. So let's see. This way, yes. This way, yes. This way, no. This way, no. It takes practice to do that, by the way. I showed you that already.
Just one question about this one.
Yeah.
It's approaching from the right, should it be approaching from the left?
This one?
No, the one above it.
This one? This is approaching from the right, going to negative infinity.
Oh, I see the plus now. Oh, never mind. Okay.
Yeah, you know what? Let me write that out too. If this and this
Then
you see
wouldn't
the-
exist.
the thing here, if we go from the right and from the left, and they both go to positive infinity, then this was your question. Yes. Sure. If the two, if this works all the time, if the left side limit and the right side limit go to the same thing, the limit exists. You could substitute in, if this is going to negative infinity and negative infinity, that would be negative infinity. So you can draw that corollary as well. Good question. Any other things for that one? Any other questions before we continue? All right, let's compute some limits. Did you get that?
Whoa, just jumped right in the next one, huh? 3 hours? Are you kidding? Jeez, dude. Alright, I just wanna make sure I'm good on this. So, goals of calculus. Find the tangent to a curve at a point. And then the other one was find the area below a curve. Of a curve, whatever. Yeah, under.
That's great. That's great. Oh, one more little note. Why was it that we can't just let Q equal P? What was the reason? Why can't we just say, oh, let's move to P?
Because there wouldn't be a difference.
Okay, there wouldn't be two actual points, it would be the same point twice, and that's the problem. We're going to make an equation aligned with that. So one little note, we can't just let Q equal P because we need 2 points to make a line. You need 2 points. That would be a problem. Here's the idea of a limit, all right? This is a big idea. Here's the big idea for limits, okay? The idea is, how close can you get one point to another without them being the same point? So let's say I have 2 points like this. Can you find some space between it? Let's say I move it over to the midpoint. Can you find some space between it? Say move it over to the midpoint. Can you find some space between it? Can you keep doing that for eternity? Between any 2 points, there's a gap. In that gap, you can fill it in with another point. Because points have no breadth. That means that even though we draw them on the board like this, they really don't have any distance between them. So 2 points can get, would you agree, infinitesimally close to each other. That means so close that you can't put anything between them, but there's still some little distance. And then you get even closer to that, and closer to that, and closer to that. Would you agree to that? So here's the idea behind calculus. It says we can get Q so close to P that there's literally no difference between the secant and the tangent. We can get it so close. We can't let it equal, but we get it so close that the secant line is the same as the tangent line. That's the idea of a limit. Isn't that kind of an interesting idea? Yes, they're different points, they're so close, doesn't matter. That's the whole idea. So the big picture for our limits is, if we let Q get really close to P, the secant will be identical to a tangent. That's it. Or approximately so close it doesn't matter. Really. If we let Q get really close to P, I'll use a Hilbert term, so I'll use a more mathy word for that just a minute. Really close to P, the secant will be identical to the tangent. Here's the idea, right? Here's the idea. Now I'm going to replace this really with a key phrase for you. The idea of really, the idea of moving P or Q really close to P is called a limit. Moving something really close without actually getting there. That's the idea of a limit. You can't understand the idea of a limit? We would say that Q would be a limiting position. That means we've got it all the way really as close as we can to P, but it never touches P. That's the idea of a limit. It gets really close. So the idea of really close is a limit. In the most simple terms. So this is it. Would you like to see an example of how to actually do this? Would it be interesting to you? Have fun. All right. So So if you remember from last time, we were talking about limits, and what we're realizing is that a limit basically says, or asks the question, what is the function doing, what's the value of the function doing as x approaches a certain number? Now, do we ever care what happens when x gets to that number as far as a limit is concerned? No, not really, just what's the function doing, where's it getting close to as we're getting close to that x value, and that's the idea here. So when we're talking about the limit of x minus 1 over x squared minus 1, that's our function, we want to find out what happens as x approaches 1. Now, why can't I figure out what happens when x equals 1? Tell me that. That would be undefined, right? As a matter of fact, it makes both the numerator and denominator 0, and that would still be undefined. We found out that is that a whole and asymptote, do you remember? That's a whole. It's going to be a whole, but ultimately this function has a whole. So what we want to find out, though, is what's the function doing as we approach that certain value? Now, one way we figured out, the only way we figured out these limits is to make out a table. And this is kind of the elementary way that you discover limits right when you first learn.
Okay. I guess I'll go over to pause on my math notes, see what I can do. It's not going to match up perfectly, but... So this is introduction to limits. The next video is properties. Properties to limits. Alright, chapter 2, limits. The topic that we will be examining in this chapter is that of limits. This is the first of 3 major topics that we will be covering in this course. While we will be spending the least amount of time on limits in comparison to the other 2 topics. Limits are very important to the study of calculus. We will be seeing limits in a variety of places once we move out of this chapter. In particular, we will see that limits are part of the formal definition of the other 2 major topics. In this chapter, we will discuss just what a limit tells us about a function, as well as how they can be used to get the rate of change of a function, as well as the slope of the line of a tangent. The rate of change of a function. Okay, as well as the slope of the line tangent to the graph of a function. Although we'll be seeing other easier ways of doing these later. We will investigate limit properties as well as how a variety of techniques. We will investigate limit properties as well as how a variety of techniques to employ when attempting to compute a limit. We will also look at limits whose value is infinity and how to compute limits at infinity. In addition, we'll introduce the concept of continuity. Now, continuity is used in the intermediate value theorem. The intermediate value theorem is an important idea that has a variety of real-world applications, including showing that a function has a root is equal to 0, whatever that is, at some interval. Finally, we'll close out the chapter with the formal / precise definition of the limit, sometimes called the delta epsilon definition. Here's a list of topics that are in this chapter. So we got tangent lines and rates of change. In this section, we will introduce 2 problems that we will see time and again in this course: rate of change of a function and tangent lines to functions. Both of these problems will be used to introduce the concept of limits, although we won't formally give the definition or notation until the next section. Okay. Section 2.1, tangent lines and rates of change. In this section, we are going to take a look at 2 fairly important problems in the study of calculus. There are 2 reasons for looking at these problems now. First, both of these problems will lead us into the study of limits, which is the topic of this chapter after all. Looking at these problems here will allow us to understand just what a limit is and what it can tell us about a function. Secondly, the rate of change problem that we're going to be looking at is one of the most important concepts that we'll encounter in the second chapter of this course. In fact, it's probably one of the most important concepts that we'll encounter in the whole course. So looking at it now will get us to start thinking about it from the very beginning. Alright, so tangent lines. First problem that we're going to look at is the tangent line problem. Before getting into this problem, it would probably be best to define a tangent line. Tangent line to the function f of x at the point x equals a is a line that just touches the graph of the function at a point in question and is parallel in some way to the graph at that point. Take a look at the graph below. So we've got a tangent line at this point and not a tangent there. Touches the graph of a function at the point in question. Okay. And this graph, the line is tangent line at the indicated point because it just touches the graph at that point, and it's also parallel to the graph at that point. Likewise, at the second point below, at the second point shown, the line does not touch the graph at that point. It does touch the graph at that point, but it's not parallel to the graph at that point, and so it's not a tangent line to the graph at that point. Okay. At the second point shown, the point where the line isn't a tangent line, we will sometimes call the line a secant line. We've used the word parallel a couple of times now, and we should probably be a little careful with it. In general, we think of a line and a graph as being parallel at a point if they are both moving in the same direction at that point. So in the first point, above, the graph and the line are moving in the same direction, so we say they are parallel at that point. At the second point, on the other hand, the line and the graph are not moving in the same direction, so they aren't parallel at that point. Okay, now that we've gotten the definition of the tangent line out of the way, let's move on to the tangent problem. It's probably best done with an example. So example 1, find the tangent line to I'll write down example 1. Find tangent line to f of x equals 15 minus 2x squared at x equals 1. Okay, so let's see. Okay, first I want to plot some points. So when you plug in 0, you're going to get 15. So when x is 0, y is 15. 5, 10, 15. When you plug in half, what do I want to plug in? -1, I guess. Plug in -1, you get 13. So about here. -2. About 11. So you can kind of see the pattern there. 1. 13. And then 2, I'm going to guess is 11. Yeah, because it's exponential. So it's looking like a downwards parabola. Like this. Okay. So we're trying to find the tangent line here. So say this is the tangent line. Wait. I don't know, something like this. And then we want to find a point that's very close to this. It doesn't actually touch. So we want to turn basically turn it the secant line into a tangent line. So we're trying to find m, the secant, the slope of the secant right now. That's x2, wait, y minus y sub 1 equals m times x minus x sub 1. It's y2 over y1, x2 over minus x1. I think that's it. Let me look it up. Yeah, okay. So, let's see. Okay, as x approaches 1, what is happening? Y is approaching, or f of x approaches 13. I'm trying to remember this from the video. Let's see. Okay, so a way, kind of like the cheap way to do it, would just be to say like, okay, so we know y1, x1, right? So y2 minus 13 over x2 minus 1. I'm gonna cheat. I'm gonna watch the video again. I wanna see the tangent problem again. It's been like 2 days since I saw
Before I go any
this.
further, did you guys understand the tangent problem? Not sure if you're okay with the tangent problem. You understand the idea of limit? Moving a point
Maybe
really
it was
close
one.
to, but
Might have
never
been just
actually getting
yesterday.
there. Again, why can't we
Maybe.
get there?
I forgot my
Get
watch.
your points. Yeah, that'd be fun. Okay, cool. Now we're ready. I'm excited. First little step off into calculus land. Do you trust me? You shouldn't. here's the goal to this problem. I want us to find the equation of the tangent line to this curve at a certain point. Specifically that one. 1, 1. Well, let's go over to 1, 1, and let's put a point there. So P is the point 1, 1.
So for me, it would be 113.
I'm going to walk you through how we're going to do this right now, okay? I'm going to walk you through how we're going to make up a tangent line using this idea. Are you ready for it? Over here on this idea, we had 2 points, right? P set in stone, you're not going to move P. What other point do we have?
Q.
We're going to make a point Q. Q. What's the coordinates for point Q? Why don't you tell me? It's coordinates for point Q.
2.
We can't use actual numbers, right? That wouldn't be very good. So I know 2, 4 would be on there, and 3, 9 would be on there, 4, 16, and so on. But I want you to use actual points. In general, what are the points for, or what are the coordinates for any point? X, Y. Very good. Okay, X, Y. So now write down X, Y, and have your eraser handy. Have your eraser handy because I'm not going to have X, Y. I want to keep this in terms of one variable. Now, using your knowledge of what the function is, what's the function? Y equals what? Wait, say it again. Y equals what? Y equals... So instead of having x comma y, would it be okay with you if I had x comma x squared? Yeah. Yes, no? Because y is x squared, right? So that won't matter. So erase that, and I want you to put x squared. Cool. All right. All right. Now we have this secant line going from P to Q. P is a fixed point 1, 1. Q is a movable point x comma x squared. Would you agree that any point on this line will have the coordinates x comma x squared? No matter what I plug in, right? So that movable point, that's going to have the same coordinates all the way down.
Okay, so to set this up kind of the same. Yeah, I did. So this would be my M, right? So I got my 1.113. This is where I'm trying to find the tangent line, and then I got x 15 minus 2x squared. That's my other point. So from here, kind of
Now we have this
forget a little bit.
secant line. Here's what we want to know. We know that the equation for a line is y minus y1 equals m x minus x1, true? What we're trying to find is the equation for a tangent line. Here's what the equation for a tangent line would be. Pay close attention. It would be y minus y1, that's the same, equals the slope, but a specific slope. It would be the slope of the tangent line, true? Whatever the tangent line slope happens to be. So the slope of the tangent line, and then x minus x1. Now, the cool part about this, I'll recap this in just a bit. The cool part about this is we already have a point. What's my fixed point that I have?
1, 1.
I already have 1, 1. So really what this comes down to is can you...
So I'll write this down. Y minus y sub 1 equals the slope of the tangent line. X minus x sub 1. If I plug in the points, 1 minus 13 equals the slope of the tangent line, x minus 13.
You find the slope of the tangent. That's why I said finding the slope of a curve at a point is the big deal for calculus. You already have the point. That's the easy part. The slope is the hard part. So we're going to try to find right now the slope of the tangent. Are you ready for it?
Yeah.
You sure? We're going to use the idea of slope of a secant. So we're going to take a break right now. We're going to come back to this in case you're just a little bit lost.
Alright, so the slope of the secant is going to be I already wrote it up there. y2 minus y1 for x2 minus x1. Yeah, so from here again, like
Here's what we've done so far.
how do you make this
This
jump
is y
again?
squared I gave it to you. We fixed one point according to my problem, that's 1, 1. We've made up another point, a movable point, q. Q is at x comma x squared. Where did x squared come from? That's because it's y. All right, great. We now know that the equation of a line is this, so therefore the equation of a tangent line would be the same exact equation. It's just we'd have the slope of the tangent line. The problem is,
Be
it's
fun.
very hard to find the slope of a tangent line without doing the limiting idea. You can't do it because there's only one point there. So we're going to have to use the idea of a secant and make it into a tangent line by moving Q really close to P. Did you get the idea? Basically doing that with this problem. So let's take a look at the slope of a secant. Our specific secant. Hey, by the way, do you remember the slope in general, the slope formula? Slope is what over what?
Right.
Okay, great. In terms of our coordinates, slope is delta y over delta x. Specifically, in terms of our coordinates, what is our slope? That's what I'm looking for. y2 minus y1, yeah, over x2 minus x1, otherwise you get the negatives of that slope. So y2 minus y1, x2 minus x1. Do you follow? How many people feel okay with this so far? Just slope formula. What we're going to do, we're now going to find the slope of our secant. We've got the secant on the board, right? The secant will be the slope, I'm sorry, the slope of the secant will be the slope from points P to Q. Agreed? Let's plug in these coordinates. We only have them on the board. Plug in these coordinates into that formula. In our case, our y2 is what? Our y2 would be x squared. What's our y1? Not x. Would be 1. What's our x2? What's our x1? Okay. y2 minus y1 over x2 minus x1. Not sure if you're okay with that. So what we have for the slope of our secant is y2 minus y1 over x2 minus x1. Are you okay with this so far? Find out where the slope comes from. There's a couple notes I want to make at this point. First, I'm reiterating a lot of stuff here. I know that I am. I'm doing it on purpose because these are the key points of calculus, all right? You need to understand what we're doing. I would hate for you to get through this class, right, and at the end of it, know how to take derivatives and integrals and have no idea what you're doing. You can be successful on just doing derivatives and integrals in this classroom. But if you don't understand what it is you're actually doing with those things, you don't even know what they are right now. But if you don't understand what you're doing, it's irrelevant. You're just doing formulas. It sucks. If you know what it comes from, what you're actually doing, I'm going to make sure you know, by the way, it's a little bit more interesting and you can apply it to more things. Do you get the picture? So right here, what we're doing, step number 1, is if we move Q close to P, this is going to become this. Do you agree? As Q, I'm going to use a new symbol here, approaches P. That means as Q gets really close to P without touching, the slope of the secant line approaches the slope of the tangent line. Would you agree with that statement? That's over here right now. You agreed with it already. Haha, I tricked you. As Q gets close to P, the secant gets close to the tangent. True? That's what this says right now, okay? As Q gets close to P, the secant gets close to the tangent. How close? It depends on how close we get these things. If we get them so close it doesn't matter, then these become so close it doesn't matter. Agreed? It's kind of neat, right? It's a cool idea. Now, the problem is, here's note number 1. Here's note number 2. This is interesting, right? Where are we trying to find the slope? What point? 1, 1. Well, and what's the x-coordinate for 1, 1? To find the slope of anywhere, you plug in that value, right? This gives you the slope of the secant line, true? Plug in 1. Plug in 1. What happens? No, you don't get 0. You get 0 over 0 is not 0. That's a big problem. 0 over 0 is undefined, right? Isn't that an issue? This is why, folks, this is the reason why you cannot have the point getting, listen, you can't get q close to p because if you plug in 1, it's undefined. That means that you now have the same point. So you can't let x equals 1, that's big time. That means double important. You can't let x equal 1. This is why we can't let q equal p, because we only have 1 point, right? You can't find the slope. It fails. It's undefined at that point. This is why q can't equal p. If it does, if you try to find the slope of the secant at that point, move q all the way down and then plug in the x coordinate. If it's the same thing, you're going to get something that's undefined because you're trying to find the difference between points that don't exist, a difference that doesn't exist. And that's going to be, you're divided by 0. There's no difference in the x-axis. That would mean you're divided by 0. You get something that's undefined. You get an undefined slope. That's a bad thing. So we can't let q get all the way to p. True? All right. What can we do? Now this is going to blow your mind. You ready to get your minds blown? Like a mind grenade. You ever seen Yes Man? Watch Yes Man. It's so fun. Had a Ripple. Y'all have Ripple? It's called Ripple. Right. Have you not seen it? That just sounded really stupid. You watch Yes Man. It's pretty funny. Now, so, next part. Gonna blow your mind. Can you factor that? In fact, learning what we knew about asymptotes and stuff like that, you know that if you have 0 over 0, it's factorable because of, well, some stuff in mathematics that I haven't bored you with yet. But if you ever have some number that makes 0, it means that that's a factor. If you have some number, the same number that makes 2 polynomials 0, it means they have a common factor. We've got a common factor here. In fact, if you were to factor this is going to give you x plus 1, x minus 1 over x minus 1. Agreed? Okay. Do you see anything that simplifies out of that?
Okay, so I remember his point here was like, you can simplify this, the domain issue's still there, but you're not actually plugging in 1. You're just getting really close to 1. For this though, does this factor? So there's a negative 13 up there. Do I gotta find the limit of this? So here, I'll find the, as x approaches 1, what does 15 minus 2x squared approach? And that would be 13. I already found that. Dang it, man. This is weird.
Haha. Now this is cool. Now this is interesting. Very interesting. What we're going to do is we're going to be able to simplify out this
What do you
thing.
do
Now
if
I
it
know what
doesn't
you're
simplify?
thinking. Well, wait a second. Can't you not simplify out a domain issue? Isn't that a problem for you? And the answer is yes and no. It would be a problem normally. However, watch carefully. Are we actually letting x equal 1? Is q actually getting to the point P? No. So is x actually equaling 1? No. We're getting really, really close. I'm talking like 1.00000 forever and then a little bitty 1 at the very end of it. Really close. But it's never actually equaling 1. So keep in mind, when we do this, we're not getting rid of we're not really altering the domain whatsoever because we already knew x wasn't equal to 1. So we have this little restraint.
Okay, I get the rest of this, but what do you do if it's not going to simplify, I guess? This is a little bit different. So we know from algebra that to find the equation of a line, we need either 2 points on the line or a single point on the line and a slope of the line. Since we know that we are after a tangent line, we do have a point that is on the line. The tangent line in the graph of the function must not touch x equals 1, so the point 1 f of 1 equals 113 must be on the line. Now we reached the problem. This is all we know about the tangent line. In order to find the tangent line, we need either a second point or the slope of the tangent line. Since the only reason for needing a second point is to allow us to find the slope of the tangent line, let's just concentrate on seeing if we can determine the slope of the tangent line. At this point in time, all we're going to be able to do is to get an estimate for the slope of the tangent line. But if we do it correctly, we should be able to get an estimate that is in fact the actual slope of the tangent line. We'll do this by starting with the point that we're after, P, 113. We'll then pick another point, Q, X, f of x. For the sake of the argument, let's take x equals 2. You will then pick another point that lies on the graph of the function. Whoa, it's got animated at the bottom. Alright, so they plug in x equals 2. We get 2, 7. Wait, that's not what I got, is it? Did I do this wrong? I plugged in 2 wrong. Oh. 15 minus 8. Whoops. Alright, well this makes the points look a little bit better. Alright, whatever. So we got 2, 7. And these are the points. So we got the secant line right here. Or wait, yeah, the secant line is the green one. And then we got the tangent line and all that. You can see from the graph that the secant and tangent lines are somewhat similar. So the slope of the secant line should be somewhat close to the actual slope of the tangent line. So as an estimate of the slope of the tangent line, we can use the slope of the secant line. Alright, that's a terrible estimate though. Now if we weren't too interested in accuracy, we could say this is good enough and use this as an estimate of the slope of the tangent line. However, we like to estimate that it is at least somewhat close to the actual value. So to get a better estimate, we can take an x that is closer to x equals 1 and redo the work above to get an estimate on the slope. We could take a third value of x even closer and get an even better estimate. In other words, if you take q closer to p, the secant line gets closer and closer. Yeah. As we move to q closer to p, the secant line starts to look more like the tangent. Don't worry about how I got the exact or approximate x slopes. We'll be computing the approximate slopes shortly, and we'll be able to compute the exact slope in a few sections. in this figure we only looked at q's that were to the right of p, but we could just as easily as use q's that were to the left of p, and we would have received the same results. In fact, we should always take a look at the q's that are on both sides of p. In this case, the same thing is happening on both sides of p. However, we will eventually see that this doesn't have to happen. Therefore, we should always take a look at what is happening on both sides of the point in question when doing this kind of process. So let's see if we can come up with the approximate slopes. We showed above, hence an estimation of the slope of the tangent line. In order to simplify the process a little, let's get a formula for the slope of the line between P and Q. That will work for any x we choose to work with. We can get a formula by finding the slope between P and Q using the general form of Q. Let's pick some values of x getting closer and closer to x equals 1. Plug in and get some slopes. I'm going to try this for myself in a minute. Okay, so make a table. So we're trying to find out what happens when 2, 3, 4, 1, 2, 3, 4. Okay. When x is 1. Well, we know it's 13 down here. So at 0.5 and then 1.5, 0.1, 0.001. Right, no, not 0, 0. We want this to increase, so 0.9, 0.999, negative 0.9, no, not even negative, 1.001, 1.1. So I'm gonna bring up the calculator. Minus 2.5 squared. 14.5. 15 minus 2, 0.9 squared. 13.38. 15 minus 2 times 0.999, 13.002, 15 minus 2, 1.001 squared. Oh wait, for 0.999 I didn't square it. So I'm gonna have to go back. 12.996. 15 minus 2. 0.999 squared. 13.004. 15 minus 2. 1.1 squared. 12.58. And then 15 minus 2. 1.5 squared. 10.5. So alright, let's say that I want to use 0.999 when x equals 0.999. So to find the secant, I'd plug in 0.999, no, 13.004 minus 13, or 0.999 minus 1. And then you get negative 4. which means the tangent line should be about -4. And if I plugged in 0.9 repeating forever for x, then it should be approaching -4. So yeah, so like for this, you can see it gets closer to -4. So if we take x's to the right of 1 and move them in very close to 1, it appears that the slope of the secant lines appears to be approaching -4. If you take it to the left, it also approaches -4. Based on this evidence, it seems that the slopes of the secant lines are approaching -4 as we move towards x equals 1. So we will estimate that the slope of the tangent line is also -4. As noted above, this is the correct value, and we will be able to prove this eventually. Now the equation, the line goes through. Oh yeah, then you plug into the equation. So the equation of the tangent line is this. Alright, I'm gonna end it there. I'll work more on this section tomorrow, and then I'll keep going with the Paul's on the math notes till I see something that I don't know yet.